Hello, everyone. This video is covering section 11.6, absolute convergence. So let's define absolute convergence, and we're going to define a couple other things as well. So let's start with a series. Okay, just our normal, excuse me. So let's start with our normal series AN. And when I say normal, that doesn't mean anything in particular. This could be any type of series, alternating series, geometric series, whatever. This could be any type of series. Okay. But we can get a lot of information about this series if we look at the series of absolute values. Okay. So let's, what do I mean by that? Okay. So we start with a series AN. And let's assume for the moment that this series has, some negative terms. So let's say our series AN, maybe that equals 1/2 plus negative 1/3 plus 1/4 plus negative 1/5 and so on. Okay. So maybe this is we could write this as, let's see. So maybe this is the alternating harmonic series, starting at 2. Okay. We could look at this series directly, and we could ask a bunch of questions like, does this series converge, and so forth. But what we could also do is we could look, instead of looking at that series, we could look at the series of absolute values. Okay, so if this is my series, let's say that this is my series AN, what would the series of absolute values look like? Well, it's the same numerical stuff, but everything's positive, right? So that I would lose that alternating sign term. Okay, so the series of absolute values would look like this, right? I would just take all of this stuff and make it all positive. Okay, I'm doing the absolute values of each term. So that's what I mean by series of absolute values. Okay. Let's give a definition, and then we'll kind of loop back to why we're doing all this. So let's consider a series AN. So maybe this series has some negative terms, maybe it doesn't. We can consider this series of absolute values. Okay. If this series of absolute values converges, then we say the original series is absolutely convergent. Okay. So that might be a little confusing. All right. So we're starting with this series, the sum of A sub n. And then we're looking at the series of absolute values. Okay. If this converges, we say this is absolutely convergent. Okay. So let's see an example real quick. We could have -1 to the power n, 1/2 to the n. So this is an alternating series. It's really a geometric series, right? This is the same thing as it's a geometric series, but let's look at it a little bit. Let's consider that series of absolute values. Okay, so when I take the absolute value of everything, what does the series of absolute values look like? Well, if I take the absolute values of this, that negative sign is going to disappear, right? And I should just be left with 1 over 2 to the n. Okay. Now, what do I know about this series? Okay, so let's look at this series. As I said, that's a geometric series, and let's say we have r, absolute value of r is less than 1. So that series of absolute values is convergent, right? This series is convergent by the theorem regarding geometric series. Okay, so this thing converges. So we could say that the original series is absolutely convergent. We could think of this as meaning, okay, we have a series, maybe it's got some negative terms and all that, and then when we take the absolute values, it's convergent. You might be asking, all right, why do we care? Why are we doing this? Why are we taking the absolute values? Well, it turns out that we can actually get a lot of information about our original series by considering the series of absolute values. Okay. So if we have a series with some negative terms, we can get a lot of information by considering this instead. Okay. We can get a lot of information about this. Okay. So my little graphic would be, maybe it has some negatives. It doesn't have, this original series doesn't have to have any negatives. It's, more interesting if it does, but whatever. Okay, so this is the little graphic I would draw. We're starting with this series. Maybe it's got some negative terms, maybe not. We consider that series of absolute values. Okay, and we figure out if this thing converges or not. Okay, and that gives us, it kind of sends information back this way. It tells us information about our original series. Okay, I haven't shown you what information yet, but for instance, we're going to see in a moment that if the series of absolute values converges, then our original series converges. And you might be saying, well, why don't we just, consider the original series? Why do we have to look at the absolute value series to see if it converges? Well, maybe this original series is kind of complicated. Maybe it's got some negatives that make things kind of complicated. But when we consider the series of absolute values, it gets simpler. Okay, so maybe it will be helpful to look at this thing, this series of absolute values, see if it converges, and then that gives us information about our original series. So it's a very useful idea to consider the series of absolute values. So as I said, we might start with some complicated series a sub n, and maybe it's got some negatives and we can't figure it out. But then when we consider the series of absolute values, it becomes much more simple and we see it converges. And so that must mean that our original series a sub n also converges. Okay, so I've stated this. Let's go ahead and, we can prove it real quick. Okay, so this is the theorem regarding the statement I just made. If the sum of a sub n is absolutely convergent, then a sub n is convergent as well. And remember what absolutely convergent means. Absolutely convergent means that this series converges. Okay, So we're just saying that if this series converges, then this series converges. Okay, and maybe it I don't know, seems intuitively clear, but it's not like it's not something that you can just take for granted. We got to show it. Okay. So if the term a sub, let's prove it. Okay, and let's just consider the terms for a second. And let's assume this term a sub n is negative. Okay, then a sub n plus its absolute value would equal 0, right? So let's say if like an equals -2, then an plus absolute value of an would be -2 plus 2, that would equal 0. And that's true for any number, okay? Any negative number. Okay? So if a sub n is negative, then an plus its absolute value equals 0. On the other hand, if a sub n is positive, then a sub n is equal to its absolute value, right? If an equals 2, an absolute value of an, that's still just 2. So on the other hand, an plus a sub n equals 2 absolute value of a sub n. Okay. So we have this inequality, okay? It doesn't matter, now it doesn't matter if a sub n is positive, negative, whatever, okay? It's always going to be, this term a sub n plus its absolute value is always going to be greater than or equal to 0, right? On the other hand, it's always going to be less than or equal to 2 times the absolute value. And if it helps, maybe consider, try this on your own, pick a bunch of numbers, pick any number you like, positive, negative, whatever, -7, positive 13, 100,000, whatever. Pick a bunch of values and try this out, and you'll see that this inequality always holds. Okay. So what does that do for us? Let's consider the series of these terms. So let's add up all those terms. Okay. Let's add up all the terms of the form a sub n plus absolute value of a sub n. Okay. Well, all the terms are greater than or equal to 0, so that series is greater than or equal to 0, right? And on the other hand, we have just shown that all the terms are going to be less than 2 times the absolute value of an. So this series has to be less than or equal to this series. Kind of think comparison test. This is kind of like a comparison test idea. Okay. And we're assuming that this series here is convergent. Okay. So since this series is convergent, then comparison test, okay. This series is convergent, or just multiplying it by a constant, that doesn't affect anything. This series is convergent. So by comparison test, this thing has to be convergent, right? And you can check, there's some conditions for comparison test, right? We need all the terms inside the series to be greater than or equal to 0, and that's true, right? We've already shown that's true. Okay. So by comparison test, this thing converges. Now there's a theorem that maybe doesn't get too much, we haven't talked about too much. This would, well, maybe it was covered by Ariel in her section 11.2 video. It would have been in that section, and that was one I missed when my daughter was born. So remember that when we have 2 convergent series, an and bn, then we can add them or subtract them, right? Like this, okay? So remember that. Okay, so what have we done? We've shown that this thing is convergent, and we know this thing is convergent, right? So now let's just kind of subtract one from the other, okay? So we have this series, and we're going to subtract away that series of absolute values. We know this is convergent, we know this is convergent, so we can do that. And when we subtract away, what we end up with is our original series, a sub n, okay? So this thing has to be convergent as well. And again, it's kind of going back to this idea that if we have two convergent series, we can add them or subtract them like this. And the result, not only can we do that, but the result will still be convergent. Okay. So if this is convergent, and this is convergent, then this thing will be convergent. Okay. So that's what we've done. All right, so just to reiterate, what have we shown? If A sub n is absolutely convergent, then AN is convergent. Meaning, okay, if this converges, then this converges. Does it work the other way too? So that's a question, an important question. If AN converges, does that automatically mean that the series of absolute values converges? The answer is no. And there's actually a really straightforward example that we've seen already. Okay, so think of the alternating harmonic series, right? We know that this converges. Why does it converge? Converges by alternating series test. And if I was going to show this on a quiz or something, you know, I got to check my conditions. But hopefully it's familiar that this converges by alternating series test. But if we consider the series of absolute values, what does that give us? So let's take the absolute value of everything. Then we just end up with the harmonic series. And this is our most famous divergent series. All right. So we have an example of a series AN that's convergent, but absolute values divergent. Okay. And there's a special name for this scenario. When our original series A sub n converges, but the series of absolute values diverges, we would say that this original series is conditionally convergent, okay? Meaning it really depends, right? It depends on those, it's kind of conditional on those negatives that might be living inside this series. Okay, so we say it's conditionally convergent. So now we can classify all of our series into three categories, and you'll see a lot of questions asking you to kind of work with these categories. So we can now take a series AN, A sub n, and we can ask, is the series absolutely convergent? Is it conditionally convergent? Or is it divergent? Okay. So let's, remember what all these mean. Okay, so absolute convergent would mean the series of absolute values converges. And that implies that my original series also converges. Okay. Conditionally convergent, meaning the series of absolute values diverges, but my original series still converges. All right. And then divergent, everything is divergent. Okay. In particular, we mean my original series diverges. That's what we mean by divergent. But if this series diverges, then that series of absolute values also has to diverge. Okay, so then we have these three possibilities. Absolutely convergent, so meaning everything, you can think of it as everything converges. Okay, so both of these converge. Conditionally convergent, this diverges, but this converges. And then divergent, everything diverges. All right, so we have these three possibilities for a series. So now our questions about a series are going to be asking typically we're going to have, well, let me kind of rephrase that. Typically, we're going to now have a series A sub n, and now we're going to be asked, is the series absolutely convergent, conditionally convergent, or divergent? Okay. So we need to figure out how to tell each of these. All right, so we need to be able to tell if a series is absolutely convergent, conditionally convergent, or divergent. So we're going to consider each of these three things separately. Okay, and really, this section is mostly about absolute convergence, so we're going to spend most of our time on this. So if we're given a series A sub n, just some arbitrary series, maybe it's got some negative terms, maybe it doesn't, whatever. How can we tell if it's absolutely convergent? There are three methods in this section. Okay, first off is by definition. Okay, so what I mean by definition is, what is absolute convergence? That's when, you know, we're starting with, maybe we're starting with the series AN. This series is absolutely convergent if this thing converges, the series of absolute values. So that's the definition of absolute convergence. So by definition, what I mean is, we're just going to look at this series and use all our previous methods to test whether it converges or diverges. And really, this is the most fundamental way to do it. I won't say easy, but the most fundamental way to test for absolute convergence. But it's really often overlooked because we're going to introduce some tests later on that are really quick and easy to use. And so people just kind of tend to use those tests and kind of forget about this, just showing it by definition. But this is a really useful tool and you're going to need it. Okay. So if we're given a series AN, how do we show it's absolutely convergent by definition? We just look at the series of absolute values and use all our previous tests or theorems to determine whether it's convergent or divergent. So an example from the book, which I think is a good one, is this series cosine of n over n squared. Okay. So how can I tell if this is absolutely convergent or not? Okay. So this is my series AN, right? And cosine can be, you know, positive, negative. It's between -1 and +1, right? So for some n, this cosine n is going to be positive. For some n, it's going to be negative. But it's not a nice alternating series either. It's not a nice series like this. Okay, you know, these aren't the same thing. So maybe this thing will be negative for 5 terms and then positive for 5 terms, and or, you know, maybe positive for 3 and negative for 7. You know, it's I haven't really written out the terms, but it doesn't have a nice alternating structure to it. Okay. So how do we determine if this thing's absolutely convergent? What we do is, I'm going to take this series and I'm going to consider the absolute values. Okay. So I'm looking at this thing directly. I'm considering that series of absolute values directly. Now, it would seem that this is just more complicated, right? I have cosine of n over n squared, and now I have the absolute value bars. I haven't really made anything more simple. But what do I know about, you know, I could write this as, this is the same as n squared is always positive. So, you know, the absolute value bars don't really have an effect on n squared. So really what I have is absolute value of cosine of n over n squared. Okay. What do I know about absolute value of cosine of n? It's greater than or equal to 0 and less than or equal to 1. So this cosine of n over n squared, this absolute value of cosine of n over n squared. Let's see. All these terms are positive and they're all less than or equal to 1 over n squared. So my series is less than or equal to this series. And what do I know about this series? It's a convergent P series. So this thing converges by comparison. So my series of absolute values is convergent, okay? We kind of had to take several steps, right? We had to look at the absolute values and then we had to do a comparison test, but this is still all by definition. We're looking at this series of absolute values and determining if it's convergent or divergent. In this case, it's convergent. Let me give us some more space here. So what we have determined is that the series of absolute values is convergent. So we say that our original series is absolutely convergent. Okay. So a quick little summary. To show something's absolutely convergent by definition, we're just going to look at the series of absolute values, and then we're going to evaluate it using all our previous tests. So we could have used, maybe not on this particular problem, but in the future we could use integral tests, geometric series tests, comparison tests, and so on. We use all our previous stuff to determine if this thing's convergent or not. If it converges, then we say our original series is absolutely convergent. If not, that doesn't mean our series is divergent. We just need to do a little more digging. Okay. The second method to show something is absolute, whether something absolutely converges or not, is the ratio test. So now we're developing these nice, convenient tests to use. So this all was just by definition of absolute convergence, right? We would like to develop a nice, convenient test to use that kind of tells us quickly whether something's absolutely convergent or not. And that's what the ratio test does. And then we're going to develop another one called the root test after this. Okay. So they're very simple to use, and people like them a lot and tend to rely on them maybe too much, but they're very, very powerful. Okay. So let's consider this series A sub n, and we're going to conduct the ratio test on it. And the ratio test, before we say what it is, it's got three possible outcomes. Okay. So let me just tell what the ratio test is real quick. If we have a series AN, I'm going to look at AN plus 1 over AN. Okay. And then I'm going to take the limit of that as n goes to infinity. Okay. And actually, I need to do absolute value of AN plus 1 over AN. Okay. And I'm going to look at what this limit is. So how would I do that? Okay, so let's say I have a series like before we even talk about what the results of the ratio test are, how do I set up the ratio test? These are my ANs, right? And we could make it a bit more interesting. Let's say we have -3 at the end. Okay. First, I need to set up my ratio test. I need to find AN plus 1 over AN. Okay. Well, first of all, what's our AN? Our AN is just the term in here, right? Okay, so AN would be n over -3 to the n. What would AN plus 1 be? That would just be the next term in my series. So that'd be n plus 1 over -3 to the power n plus 1. Okay. And now what's AN plus 1 over AN? What's the absolute value of that? Okay. Let's set up that fraction. Well, in this case, AN plus 1, okay, is this. I'm going to divide by this, which means multiplying by the reciprocal, right? So AN plus 1 over AN would end up being n plus 1 over -3 to the n plus 1 times what? -3 to the n over n, right? Absolute value. Now, once we have this, what we usually do is we kind of get similar stuff over similar stuff. So that n plus 1 is similar to this n, right? And this rearrangement doesn't affect anything, right? I'm not changing anything. Okay. So I've just rearranged it a little bit. And now this is going to make finding the limit really a lot more simple. Okay. Remember, I want to find the limit as n approaches infinity of this. Okay. So I want to find the limit of this thing. Okay. And now that it's rearranged like this, maybe finding the limit is easy. I can just kind of consider the pieces individually. We could simplify first though. Okay. N plus 1 over n, and then this -3 to the n over -3 to the n plus 1, that simplifies as -1 over -3, right? And then I'm taking absolute value, so this negative gets kind of canceled out. So what I have is this. And then what's the limit of this thing? Well, I could simplify that some more. Okay. This is just a constant, so I can bring it outside my limit. And then the limit of this thing is 1. So I have 1/3 times 1. So the limit is 1/3. So that's the kind of machinery of the ratio test. And now what this limit ends up being, that's going to give us our kind of information. Okay. So now let's go back to the notes. Okay. So we've seen what the ratio test is. It's just the an plus 1 over an, absolute value. Always do absolute value. Now there's 3 results of the ratio test. If that limit is less than 1, then the series an is going to be absolutely convergent. Remember, that means that the series of absolute values converges. If the limit is greater than 1, then the series diverges. Okay? And if the limit's equal to 1, the test is inconclusive. Okay? We could prove this real quick. It's a little technical, but it's in the textbook, and I agree with the textbook that I think it's kind of within your understanding. Okay, so let's kind of show case 1 first. Okay, let's assume that this limit is less than 1. Okay. What does it mean when the limit's less than 1? Okay, if the an plus 1 over an, if that limit is L less than 1, eventually these terms, maybe they're over here, but eventually they're going to get very close to L, right? So in particular, they're eventually going to be less than this green number R. Okay. That's what this graphic is trying to show. Okay. And what we're going to do is we're going to kind of compare our series to a geometric series. Okay. So there's some index big N such that an plus 1 over an is less than R if n is greater than or equal to big N. Okay. So eventually that ratio is less than R. Okay. And when that's true, okay, I have an plus 1 over an is less than R. So let's just multiply both sides by an, and I would get an plus 1 is less than an times R. But if the same thing is true for an, then a sub n is less than a sub n minus 1 times R. So we could have an plus 1 is less than absolute value of an times R is less than an minus 1 R squared. And we continue in a similar manner. So what does that mean for our series? Okay, we're talking about this ratio an plus 1 over an. What does that tell us about our series of absolute values? Well, let's try writing out our series. Okay, if I wrote out this series, kind of long form, what would it look like? It'd be this absolute value of A1 plus, you know, a bunch of terms all the way up to that big N index. And then it would keep going to infinity. But for all these terms after big N, we know AN plus 1 over AN is less than R. Okay. So for all, like for this AN plus 1 term, okay, I know that's less than A sub N times R. And I know this term is less than A sub N R squared, and so on. So from here on out, I kind of get this nice geometric series. Okay. So these first n terms, maybe there's like 100,000 of them or whatever, maybe there's a lot of them, but it's just still a finite number of terms, and I can add those up, and they're always going to add up to a finite number, right? So this part's always finite. Okay. And then from here on out, what is this? This is just becomes a geometric series. Okay. We can kind of factor out that A sub big N, and then we have a series R to the power N. Okay, and that R is less than 1, right? So that's a convergent geometric series. Okay, so we have a finite number plus a convergent series, so that's going to be convergent. So we see that the series of absolute value of AN is convergent by comparison, right? Because our original series is less than or equal to that convergent thing. Okay, so that just shows this kind of first point of the comparison test. If that limit's less than 1, then the series is absolutely convergent. If the series, if that limit of that ratio is greater than 1, then the series is going to be divergent. Okay, and really that's just going to be by comparison test. So let's assume the limit's greater than 1. Then eventually we're going to have, all these ratios are greater than 1. And so in particular, we say AN plus 1 is greater than AN. And so AN is increasing, okay? And so it's got to get, that means it's getting further away from 0, right? Since all of these are positive. So the absolute value of A sub N is increasing. It's getting farther away from 0. And that means the original term, these have to be getting farther away from 0, right? So what does that mean? It means our series is divergent by divergence test, because these terms do not converge to 0. They're getting farther away from 0 as n goes to infinity. So that shows point 2. And then point 3, the fact that this test breaks down when the limit's equal to 1, well, that's too complicated to show. But just remember these 3 cases. All right, we do our ratio test, which I've shown you guys how to do now. If the limit's less than 1, the series is absolutely convergent. If the limit's greater than 1, the series is divergent. Okay. If the limit's equal to 1, the test is inconclusive. Okay, that doesn't, we can't, if the limit's equal to 1, we have to dig deeper. We got to do some other tests to figure out what's going on. It could be anything. Yeah, so if I was going to prove point 3, I would show you a series that, well, let's not get into it. So if the limit's equal to 1, it could go either way. So let's see some examples of the ratio test in action. And we're going to start using factorials more, okay, starting in this section. So I'll post a video on how to work with factorials. And I'll post it right after I post, or I'll make it right after I make this video. So it should be up by Monday afternoon. So if you want some clarification on factorials, I would pause here and check out that video if it's available. As I said, I'll post it by Monday afternoon, so you guys it should be available by the time you're watching this. Okay. So go ahead and watch that if you need, or look it up, and then I'll kind of assume you know how to work with factorials. Now, let's try a ratio test on this series. Okay. So first of all, what's my an? That's -1 to the power n over n factorial, right? And what's my an plus 1? That'd be -1 to the power n plus 1 over n plus 1 factorial. Okay. And so let's look at our an plus 1 over an. I'm dividing this by this, which means multiplying by the reciprocal. Okay, so my an plus 1 over an is equal to this thing. And now let's kind of regroup similar stuff with similar stuff and simplify. Okay, I have this thing. And simplifying, we'll get this. And then how does n factorial over n plus 1 factorial simplify? This is where that skill from the video comes in. That simplifies as just 1 over n plus 1, right? And then the absolute value cancels everything out, right? Or not cancels everything, but cancels out that negative. So we have this. So that's our an plus 1 over an. Okay. What's the limit of that? Well, it's the limit of n1 over n plus 1 as n goes to infinity. So that limit's equal to 0. So what does our ratio test tell us? It tells us that our original series is absolutely convergent. And if I was doing this on a test, I would show all that, and then I would make sure to include the words by ratio test. Let's see another example. I would try this on your own first. I believe this is directly from the textbook as well. Okay. I'll kind of do an abbreviated version real quick. An plus 1 over an. What would that be? That'd be n plus 1 cubed over 3 to the n plus 1. Okay. Oh, and we got negative terms here. I've got the -1 power n plus 1. And then we'd have 3 to the power n over -1 to the n cubed. Simplifying everything and kind of regrouping it, I'd have n plus 1 over n cubed. -1 times -1 times 1 over 3. Okay. What's the limit of that? Hopefully, well, in this section, you guys will get practice doing limits. Okay. Let's see. If we go ahead and cancel out that -1 with the absolute value, an plus 1 over an absolute value is equal to this. You can just drop the -1. So the limit is equal to 1/3 times this limit. What's the limit of this thing? What's the limit of this? it's equal to, well, the limit of this piece is 1, and I got 1/3 on the outside, so the limit's equal to 1/3. Okay. You guys don't see how this works, you know, if how that limit works, you need to review your limits a little bit. Limit's equal to 1/3. Okay. So again, the limit's less than 1, so our series is absolutely convergent. By ratio test. Okay, so let's summarize what we know about the ratio test. We do the ratio test. We set up our an plus 1 over an absolute value. We take the limit as n goes to infinity. There's 3 possible outcomes based on that limit. If the limit's less than 1, our series is absolutely convergent. If the limit's greater than 1, the series is divergent. And if the limit's equal to 1, the test is inconclusive. Now, note none of these possibilities say anything about conditionally convergent, okay? We cannot use ratio test to show something's conditionally convergent, okay? We'll cover that later in the video. Let's move on to root test. Root test is very similar to ratio test. So let's kind of look at the machinery of root test, kind of similar to how we did with the ratio test. Okay, so I'm starting with this series from 1 to infinity, a sub n. What is the root test? What I'm going to do is I'm going to take the absolute value of my an, and then I'm going to take the nth root of it. All right. So that's kind of the starting point of the root test. So an example, let's say I have let's say I have this series. This is kind of a complicated series. Let's say I want to execute the root test. Okay, before we even talk about what the root test is saying, what's the machinery of the root test? Okay, this is my an, right? So I want to take the absolute value of an. Well, what's the absolute value of an? The only thing that's going to change is that negative is going to get canceled out, right? Okay, so that's my absolute value of an. And the next step is take the nth root of absolute value of an. So I need to take the nth root of that stuff. Okay. Well, I have an nth root and then I have a power n. So what happens with those? They just cancel out nicely, right? Okay. All right, so that's my nth root of an. And then similar to the ratio test, I'm going to be considering the limit of that term. So the limit, this limit is equal to the limit of this thing. And what is that limit? Equals 5 over 3. And then like with the ratio test, based on what this limit is, we're going to get some conclusions. Okay, so let's go ahead and see what those conclusions would say, now that we know how to kind of execute the machinery of the root test. Okay. So again, there's 3 possible outcomes, and they're almost identical to the ratio test. Okay. If that limit of that root test, if we do the root test and the limit's equal to L, which is less than 1, then the series is going to be absolutely convergent. Okay. So our series will be absolutely convergent if that limit's less than 1. If the limit is greater than 1, the series is divergent. And if the limit is equal to 1, we again see that the test is inconclusive. So an example, let's use this example. Okay, notice I don't have any negatives in this series, and that's fine. We can when we're talking about absolute convergence, we don't have to have like an alternating series or a series with negative terms. We can talk about a series with all positive terms. So we don't have to have negatives. Okay. So let's use the root test to figure out if this is absolutely convergent. Okay. So first thing I want to do is I want to find absolute value of an. Well, this thing's positive, right? So absolute value is just the same thing as an. Okay, so that's my absolute value of an. And then I want to do nth root of an. Okay, so that's going to be nth root of this. Again, the power of n and the nth root cancel out nicely. And just a quick tidbit, this is usually when we're going to use ratio test or root test, excuse me. We're usually going to only use root test when there's like a obvious power of n in there. I won't say that's the only time we're going to use it, but that's like the most common time we're going to use it. In most other circumstances, the ratio test is easier. Okay. So this is my nth root of an, absolute value of an, and now I want to consider that limit. Okay, what's this limit? It's equal to 2 over 3, which is less than 1. So we see our series is absolutely convergent by root test. If the limit was greater than 1, our series would be divergent. If the limit was equal to 1, the series would be, well, the test would be inconclusive and we would have to do some more digging. And that kind of brings us to conditional convergence, okay? A lot of times, all right, so we've seen 3 methods to test for absolute convergence. And remember, when are we doing this? We're going to be given a series and we're going to be asked, is it absolutely convergent? Is it conditionally convergent? Or is it divergent? Okay. So far we've seen how to tell, you know, we've seen how to show it's absolutely convergent, right? We do it by definition, or we do the ratio test, or do the root test. Okay. What about conditional convergence? Okay, conditional convergence is a little more complicated, and maybe a hint of when something's going to be conditionally convergent is maybe we try the ratio test or the root test and we get that inconclusive limit, like maybe our limit's equal to 1. Maybe that's a suggestion that our series is conditionally convergent. Okay, it's not a rule, right? That okay, it's not always going to be conditionally convergent if that limit's equal to 1, but maybe it's an indication. Okay. But we need to check. So how do we check if something's conditionally convergent or not? Okay. First of all, let's recall the definition of conditionally convergent. We say something's conditionally convergent if the original series converges, but the series of absolute values diverges. So to show something's conditionally convergent, we just need to prove these 2 things. We need to show that the original series converges and that the absolute values diverge. Okay. So it's kind of like by definition, if you want to call it by definition. We need to show these 2 things, and ratio test and root test won't work. You know, in these cases, when we're trying to show something's conditionally convergent, usually the ratio test, root test are going to say limits equal to 1. Okay, that doesn't tell us anything, right? Okay, so we're just going to have to throw those out the window. So let's be very clear what I mean. Okay, so if we want to show the series is conditionally convergent, first thing we do is we look at the series of absolute values directly and show it's divergent. Okay, so not using ratio test, not using root test, we're going to look at just that series of absolute values, and we're going to show it's divergent. To do that, we can use our previous knowledge like integral test, p-test, etc. All right, so we're going to show that series of absolute values is divergent. And then second, we're going to look at the original series and we're going to show it's convergent. All right, and we're a lot of times going to use alternating series test for that. Okay, so let's look at this series, -1 to the power n over ln of n. What if I want to show that's conditionally convergent? you might develop a kind of intuition for when something's going to be conditionally convergent. But let's say let's say first, maybe the question was phrased like this: is the series absolutely convergent, conditionally convergent, or divergent? Okay, so maybe the first thing you do is you do like a ratio test or root test. Okay, so you do ratio test, and you would get, let's see, try the ratio test on your own. You should get this for your an plus 1 over an. And then you take the limit of that, and you should get the limits equal to 1. Okay, so it's that inconclusive case. Okay, so maybe that's a indication that this isn't absolutely convergent. So maybe that gives us a hint it's conditionally convergent. So what do we need to do? First, I need to show okay, so we want to show the series is conditionally convergent. So we need to show those two things, right? Well, I'm going to look at the series of absolute values first. Okay, so when I look at the series of absolute values, I get this series. Okay, and I need to show this is divergent. And actually, you know what? Let's make our life a lot simpler by starting this at, how about 2? That doesn't change anything about the ratio test. This would still be 1. Okay. All right, so now we're at this series. Okay, we have a series of absolute values. I want to show it's divergent. How do I show it's divergent? I could do interval test, right? I'll just say divergent by interval test. Scratch that. It'd be a lot easier to do divergent by comparison test, right? This is going to be greater than or equal to the series, let's see, 1 over n, right? And yeah. So divergent by comparison test. Okay. I'm going kind of fast on this just to make this video as short as possible. Verify this on your own. This series is definitely divergent. If I was going to do this on a test, showing it, I would need to show step by step that this was divergent by a comparison test or whatever other test. So I'm skipping some steps here. Okay, but the idea should be clear. Okay, we showed this series of absolute values is divergent. Okay. Then I look at the original series. All right. I need to show that this is convergent, and this is convergent by what? Alternating series test. And again, I'm skipping some steps in between here. I would need to show all those on a test, but it should be convergent by alternating series test. So I have my two conditions, right? I've shown that the series of absolute values diverges and the original series converges. And that's the very definition of conditional convergence. So to wrap up this problem, if I had this problem on a test, I would have a sentence like this. I'd say series of absolute values diverges and the original series converges. So the series is conditionally convergent. And again, this wrap-up sentence is important. You should have that. Okay. And really that covers all the conditional convergence, showing all the series that are conditionally convergent. We have to show them the exact same way, it's the exact same steps. We look at the series of absolute values, show it's divergent, look at the original series, show it's convergent. Okay. The only thing that's going to change is like maybe the tests we use. Here we use comparison tests and alternating series test. Maybe those will be different in different problems. but the basic layout is the same. Okay. Thought there was something else I wanted to say about conditional convergence. Can't remember. So that covers conditional convergence. Now, what's the last thing we need to do for our problem, right? Remember, we're kind of working on the assumption that we have a problem like this, and we're asked, is it absolutely convergent, conditionally convergent, or divergent? So we've seen how to do these two. What about divergent? Well, when we covered absolute convergence, like the ratio test and root test, that could show divergence, right? If the limit was greater than 1 for ratio test or root test, the series is divergent. Okay, so we have, we can show divergence using ratio test and root test, possibly. Okay, and we can also use just all our old material like divergence test and integral test and so on. Okay, we can use all that to show our series is divergent. Okay, so if I have a series and I want to show it's divergent, okay, maybe I can do ratio tests on this. I can do root test, and I can also use all my other old techniques like divergence test, integral test, and so on to show it's divergent. Really, the hard part of this section is showing absolute convergence and conditional convergence. Okay, that's it for the material of this section. It's a lot. I think this video is probably going to end up being pretty long, and it's kind of complicated. So I will do a problem video for this section. It's just to get you guys seeing a lot of examples. Good luck.